chat live stream, you should be seeing my iPad. And why did it screw things up like that? I don't know. Let's see. Okay. Sorry, I'm just trying to figure out what exactly is going on there. Alright. Would you recommend Windows or should I SSH into Labs? It doesn't really matter. We're going to use, you can just use Eclipse or IntelliJ as your IDE. You don't need SSH or the terminal for this. You can just follow along with the IDE right away. Cool. I'm hoping that the Twitch live stream is more stable now. If you can just confirm that on the Zoom chat so that I know that the recording will be properly correct at the end of the lecture. Yes, it looks good now. Cool. If you have any problems during the lecture, just ping me on the Zoom chat that we have so that I can fix it right away rather than waiting until the end of the lecture and realizing that I have a mumbled recording, like I actually did in 229 last semester a couple of times. One time I forgot that the mic was actually off for the whole lecture and I just had video without any audio, which was kind of useless and beats the whole purpose. Alright, so in our previous lecture we went through a few call graph analysis algorithms in an increasing order of precision. So we went through class hierarchy analysis. We've seen how we can create a call graph or construct a call graph for a program just by looking at the class hierarchy of the given program. So seeing what classes we have, what is the inheritance relationship between those classes, and deciding which methods are going to be called at a given call site just by looking at that hierarchy. This is really imprecise because you're going to get a whole bunch of classes that this method may dispatch to, this method call may dispatch to, without them being even instantiated or even present at any given runtime path of the program. So to refine that result a little bit more, we've seen RTA, rapid type analysis, that refines the class hierarchy analysis results by looking again at the class hierarchy, but only filtering out any classes that are not instantiated in the program. So looking at all the instantiations or object allocations in the program and only focusing on those objects that are allocated and looking at their hierarchy rather than the hierarchy of the whole program. So that gives you a little bit more precision. You do a little bit more work in the analysis, but it's still fast enough that you're not doing any kind of data flow analysis. The third analysis algorithm that we have seen is VTA, or variable type analysis, where you are actually also able to track variable assignments and assignments of pointers across the program. And to construct this call graph, one of the drawbacks of VTA is you need to start with an initial call graph, usually a CHA or an RTA call graph, so that you can bootstrap the type assignment graph or the type propagation graph in the program, so that you can figure out exactly where the types are allocated at and how they are propagated across your program through assignment statements. The second step that we do is that we collapse strongly connected components so that we get rid of any cycles in our graph. So we get directly a cyclic graph or a DAG that enables our analysis to terminate properly and finish the analysis to enable the analysis to terminate. Otherwise, the analysis will just keep running in infinite loops. One drawback of VTA, or a couple of drawbacks for VTA, is that you need an initial call graph to start with. And the second thing is that it does not track any kind of data flow throughout your program. So to get over these, or to overcome these two limitations, we have seen the last data flow propagation-based call graph analysis in the SOOT analysis framework called Spark. And for that, instead of building a type assignment graph, we have a much richer set of information that we propagate from one statement to the other. And in terms of the excuse me, in terms of the pointer assignment information. So we're going to track pointers from one statement to the other and how they may be assigned to each other, how they may be passed through as arguments to method calls, and so on and so forth. You know, we've seen the differences between all those call graph analyses, and we have went into more details with how we can build a pointer assignment, how the Spark analysis algorithm works and operates in SOOT. The last bit of our last lecture was to figure out or to talk about something called on-the-fly call graph construction. So what we have talked about so far is where we have a program, we scan the program, you figure out exactly at a given call site how we're gonna actually, what are the potential methods that will be called or may be called at that call site. But is that really how realistic call graph analysis work? So let's find the answer here. So what is really the call graph analysis is after? What does it want to compute? It wants to compute basically two things. The first thing it wants to compute is the purpose of a call graph, determining target calls. So give me a call site and I'm going to be able to tell you which calls or which targets this call site may have, which methods it may target. But to be able to do that, it also needs to perform a pointer analysis or a points to analysis. Because if you do a points to analysis like we did with Spark last lecture, you're going to be able to understand or to determine or compute for every variable in the program what are the pointers that it may point to at any given point, or what are the allocation sites or object allocations or references that it may point to. And if you know that, and you have a call site that has this variable as a receiver, you can tell exactly based on those objects which potential methods could be called at that point. It would basically be the methods that have the same signature at the call site that is declared in one of those objects, or the type of these objects. All right, so we know we need to do two things, right? We need to determine target calls, we need to compute points to analyses. So how do we do that? Well, obviously we need to compute call edges. So this is one relationship we need to compute. Call edges will determine what methods are reachable in the call graph or not, or in the program or not. Because any target of a call edge, that means that this method, the call graph will determine that this method could be called, so it would be reachable. I can reach that method from the entry point of the program. And if you reach a method from the entry point of the program, that means you are going to compute also what other methods would be outgoing from that method as well. You're going to process call sites from there. So call edges and reachable methods, sort of these two relations affect each other simultaneously. All right. So we just said that to determine those call edges, we need to compute the points to sets, right? Because those points to sets will determine or will identify the objects or the allocation sites, that variables that could be used as receivers of the call at any point in the program. So we need to compute points to sets, and that would affect the computation of the call edges. Now, if you remember from our previous lecture, we said that every relation or every statement that we are processing in a data flow or a propagation-based call graph analysis would induce certain constraints, right? So these are going to be called the points to constraints. So if you assign a variable to another variable, then the points to set of the right-hand side of the assignment will flow to the points to set of the left-hand side of the assignment. So if I say x equals y, the points to set of y will flow to x. If I also say x.f equals y, again, the points to set of y will flow to x.f. And what do I mean by flow to? It means that in the computation of the join of the facts in our lattice, we're going to do the join operator, and the join operator is going to be defined by the union operator, the set union operator. so that we don't overwrite old information. We just keep adding and racking up information as we go. We don't want to lose any information from before. We will see actually later in the course that this is not always the case. There are some cases where we want to forget old information when we know for sure that we are not going to use that information anymore, or when we can prove or know for sure that this information is no longer true. But for now, we're just going to use the union operation. So these constraints are two sets of constraints, these points two constraints. There are constraints that are intra-procedural within the method that will tell you the statements within the method, how they might affect the pointer assignments in your program. It's kind of similar to VTA, what it is doing. There are also inter-procedural constraints that happen due to method calls. So you assign your argument to the formal parameter of the call and then the return variable of the method to whatever on the left-hand side of the assignment of the method call in the callee method, in the caller method. So you need to handle both inter and intra-procedural constraints. All these relationships, they are dependent on each other and they affect each other. So there must be a way to solve for a system that contains all those four relationships together. And this is what on-the-fly call graph construction is. It means that we need to come up with an algorithm that will solve for all these four relationships together, given that they are going to affect each other and given that solving for one of them may lead to solving more constraints in some other relationship. So let's see how that algorithm actually is going to work. And this is really the recipe for any standard call graph algorithm that you're going to see in an analysis framework out there. All right. So the first point is I need to bootstrap or initialize my analysis. So where am I going to start? Well, I'm going to start at the entry points of the method of the program. In a language like Java or Scala or Python or C++, this is kind of relatively easy because it's just going to be whatever your starting main method is. What is the main entry point of the program? It might be more than one if you have more than one main starting entry point in your program, but typically it's just one of them, the main method of your program. So we're just going to add that to your work list and add it also to the list of reachable methods. This step gets very challenging when you're talking about frameworks like Android. You have an application, you have an app. Like, what exactly is the entry point of this app? It basically means nothing. There is no main method. There are basically event handlers that are scattered all over the place, and they get called whenever certain actions are done on the phone. Whenever you swipe left, swipe right, I don't know, hard press on the touch screen, light press on the touch screen, you type something with your pen or stylus, or you just speak out something to your phone. So these kind of things in modern mobile devices specifically, they are not that typical. They are not the same standard way of doing things in the old days in a typical programming language. Same thing if you're using a watch, for example, or a smartwatch, or any other type of smartphone. It's kind of the same thing. But generally speaking, you need to figure out what those main entry points of your program is, add them to your work list and the list of reachable methods, and move on from there. So how are we going to move on? We're going to again have one of those data flow analysis algorithms like we have done with the monotone framework. So we're going to see, this is our second work list based algorithm that we're going to see in the course. So we're going to repeat until that work list is going to be empty. Pick any reachable method from the list, just pick one of them, and process that method. How are we going to process that method? We are going to process it by finding all the allocation sites of the method. So first, find all the allocation sites. Propagate those allocation sites across the pointer assignment graph edges. So we assume that we already have created a pointer assignment graph. Then re-resolve all the relevant calls in the set of reachable methods based on that new information that you may have obtained based on the updated points two sets. So you need a couple of things here. You need a mechanism that will tell you whether those points two sets have been updated or not. You need a mechanism that will tell you here are the reachable methods that are relevant to those updated points 2 sets, and now go re-resolve them. What does it mean re-resolve them? Means just add them to the work list to be processed again. So there might be some repetition there, and again, one of the key things into making these analyses scalable is how much repetition is done, and how we can eliminate that as much as possible, so that we can analyze as many methods as possible within the same given limited time that we have for the analysis, or the limited resources that we have for the analysis. Now, after re-resolving relevant calls, if you find any new reachable methods, just add them to the work list, and also add them to the list of reachable methods. So first, you're going to pick one reachable method from the list, then you're going to find allocation sites, propagate those allocation sites across the PAG, or the pointer assignment graph, re-resolve methods based on the new information that you may have obtained by propagating things along the pointer assignment graph. If you find any new reachable methods, add them to the work list to be resolved later, and add them also to the list of reachable methods. So far so good? Fair enough? Any questions about on-the-fly call graph construction algorithm so far? Thumbs up, thumbs down, don't care, anything. Cool. All right. So far, so good then. Okay. So if we're all on the same page, then let's actually run this algorithm on a piece of code. So right now we are seeing in front of us an example from a Java program. So you have a bunch of classes a bunch of classes enclosed in a main class, and we have a public static void main method, a main method, and we are going to create that on-the-fly call graph. We're going to construct it on the fly. So I'm going to ask you a few questions along the way, and I would like some help from you to be able to construct this call graph. Are we all ready? All right. Let's get to it then. So, first step is pretty easy. I'm giving it away. We're going to start with the main method. It's going to be our entry point. We have a work list. You add your main method to the work list. You add the main method to the set of reachable methods. And down here, I'm going to have the points 2 sets, right? Any points 2 sets that I care about. So I'm going to resolve my main method. I'm going to add it to, and up here, I'm constructing the call graph. So right here, I have my call graph. Oh. Right up here, I have my call graph. Down here, I have my points 2 set. And maybe I can move this aside. No, I can't. Okay. All right, that's fine. And here I have my work list, and here I have my reachable method. So if I'm going to analyze that method main, the first thing I'm going to do is I'm going to find my allocation sites here. So sorry, the first thing I'm going to do is I'm going to pick an element from the work list. I only have one, so I just took main.main, so that main method that I have. Then I'm going to find all the allocation sites in the main method. So those allocation sites, I only have one of them, a equals new a, and that basically gave me the points 2 set of the variable a, which is going to be the allocation new a, right? So I'm going to just do the first iteration, and then I'm going to need your help from there on. So in the main method, I'm just going to call main.main, and this is going to call a.init. So a.init is that static class a. And now that I have a target of a call edge in the call graph, that makes this target reachable. So I'm going to add it here to the set of reachable methods. And since I have new reachable methods, I'm going to add those to work list. I only have one of them here. So that's why a.init, or the constructor of a, is added both to the reachable set and the work list set. All right? So now with that second statement. So here I have a.foo. So pretty simple. I'm just going to look up what the points to set of a is. And I'm going to see that the points to set of a is new a. So a.foo will dispatch to just a.foo, right? So I'm going to add this to my main method. What do I do next now? Now that I have added a.foo to my call graph from main.main. What is my next step? Also, if you have any questions before you want to give an answer, you can ask me right away. Add it to work list and reachable. Right. So we're going to add it to the work list and we add it to the reachable method, right? Because it's a target of an edge. It's a target of an edge here. So I need to add it to here, the reachable set, and then I'm going to add it also to the work list. So I'm going to do that. So I now have a few more things to process. First, I'm going to process a.foo. So what does it mean when I process a.foo? I'm just going to look at the body of that method foo, and I'm going to see that a, which is the variable, is being assigned a new allocation. So looking at the allocation size, I'm going to see new b. Now remember, having that, I'm constructing the allocation side b. So I'm going to add b.init both as a target of a.foo. And if I look at b here, b extends a. So that means that the constructor of b, or b.init, is going to call also a.init. And now that I'm going to add all the targets of the edges that I'm adding to the call graph, to the reachable set. So b.init, I just added it here. A.init, well, it's already there, so I don't need to add it again. And now I need to update the points to set of a. So now, since I'm doing the join is basically the union, so when I say the points to set of a is equal to new a, and I have the new points to set of a being joined with this, so points to set of a join new b, to find what their least upper bound in the lattice would be. So this is going to be points to set of a union new b, which will give me basically new a comma new b. And this is exactly why we have this points to set down there. All right. So now that we have this, what do we do next? We said we're going to find allocation sites. We did. We're going to add methods. We are going to propagate those pointers across the pointer assignment graph. We did. So we updated the points to set of a. We're going to add any targets or re-resolve methods here. Re-resolve reachable methods based on the new information, and we're going to add the targets of the edges as reachable methods. So one new method here that we're going to add is b.init, but it really doesn't do anything. So we are not. This b.init that we're going to add here doesn't do anything. So we go back again to the second statement here, a.foo. Even though it is the same method call as a.foo here, but it's on a different line, so we're going to treat it as a different method call. And we're going to get to actually that point exactly in about 2, 3, maybe 4 lectures or 3 lectures when we talk about context sensitivity. We're going to study this more extensively, how we can actually differentiate between calls to the same method from different points in the program, or calls from calls to the same methods from different points in the program. There are multiple ways where we can handle this. So when we have this second call to a.foo, the interesting thing is I would have to actually re-resolve that call again, even though it is the same method and I already computed that before to be a.foo, but I don't know, maybe the pointer a now has more information in it, right? Aren't the functions also different? Like, which functions are you referring to, Ridwan? Like I'm saying the call site here is basically the same as the call site here. You're calling the same method, as in the same signature, as in having the same receiver for the call A and calling the same method foo, but we don't know which foo it will dispatch to. And we're going to see exactly right now why this is going to be the case. So in the first call, we only had the points to set of A containing new A. Right now, the points to set of A has both new A and new B. So when I call a.foo at that point here, I actually have two methods that this may dispatch to. It may dispatch to a.foo, which I already have in the call graph, so I don't need to add it again, so that's done. But it may also dispatch to b.foo, which now is a new method that I'm going to add to my call graph. And once I do that, after the first a.foo, A has an, yeah, exactly. So A is going to have an object B, and this is exactly what I'm doing now. So A is going to have an object B, and once it has that, it will be added to the call graph. And once I add it to the call graph, I have now one more method to resolve, and I have to process that. So how am I going to process that? Well, I'm just going to add it to the work list, add it again to the set of reachable methods, and I go ahead to the next iteration of the work list algorithm, and I'm going to pick that method from the work list, go there, figure out that this method body is empty, so there are no allocation sites to capture or propagate or re-resolve or do anything at all, and that would be basically it, because I'll be done with my work list algorithm at that point. And now I do have my call graph at the very end. So this, after the work list is empty, I do have my full call graph. I have the main method. It may call a.init or a.foo or b.foo, and if I call a.foo, I will call b.init, which eventually calls a.init. And if I track all the targets of edges here in this call graph, these will be my reachable methods, which you can deduce from the call graph, but it's handy also to having this as well. Yep, exactly Ridwan. Yep. So far so good. Any questions about on-the-fly call graph construction? All right. So again, to quickly recap call graphs, there are multiple ways to generate a call graph from the perspective of an increasing order of precision, class hierarchy analysis, rapid type analysis, variable type analysis, and data flow or propagation-based call graph analysis, which is Spark in the Soot analysis framework. We have talked about all four of them and how they are different from each other. We've also talked about on-the-fly call graph construction in today's lecture. And next up, after we have a short break, we're going to actually see some hands-on experience with call graphs and how they actually look like in real life. So I'm going to change the scene in a minute or so, in a couple of minutes when we're back, to be my Eclipse IDE. And then we'll see. Hopefully the demo won't blow up as it usually does when you actually get to do it live. So I'll see you I'll just have a break now. It's 1:04, so maybe we'll get back to it. It's almost 1:05, so we'll get back at 1:10 p.m. I'll leave the Zoom call going. I'll leave the stream going. If you have any questions, just ask me on the Zoom chat. voice or text at this point, I'll get back to you, and I will get down to prepare the demo for the second half of the lecture today. In the points to set A, were we not sure that it no longer points to new A after A to fool's gold? So why did we still keep it in the set? So the question here is, let me get back to that here. The question here is, if I understand this correctly, so after the, let me grab my pen here. So the question here is, after this statement, don't we already know that this new B here will overwrite the new A that we had from before, right? And if we know that, why are we keeping both new A and new B to be potential objects that points to set of A may point to? And the answer is the following. It really depends on what you want to do in your analysis. Like if I'm saying that the points to set of A at any point in the program is going to be only new B, right? If I remove this and say it's only going to be new B, then I'm wrong, right? Because there is a point in the program where the points to set of A is only new A, it doesn't even contain new B. So it is not correct to say that the points to set of A at any point in the program is going to be either just new A or just new B or empty. But the more safe, or the safe solution, or the safe over approximation of the result of the pointer analysis for the points to set of A would be to say that the points to set of A is the set of new A or new B. Right? Again, think of it as your lattice of things. So you can either say that the points to set of A is empty, you can either say it's new A, you can say it's new B, or you can say it's new A, new B. Right? So if you say this only, you're missing also the other scenario here. If you say this only, you're missing that scenario here. But if you say this, then this is a safe over approximation of both scenarios that you may have in the program. We're going to see in 2 or 3 lectures how we can actually get around that and have the result of this analysis to be a little bit more precise than it is right now. To say exactly at a certain point in the program, this is going to be the result of my analysis, rather than having it so generic that it may yield imprecise results. But we're going to build that step by step as we go. So I hope that answered your question, Mohammed. All right, cool. So let me just get my Eclipse setup here ready. And of course, it doesn't see my project properly. So just give me a second to import it here. Hands-on, open. Oh, okay. Colgraphs. Right. All right. Sorry, I'm just doing some boring. Setup that for some reason used to work but now doesn't anymore. There we go. Need to add this here and finish. Hopefully this will work. And now Eclipse decides not to see my project. Sorry about that, folks. Alright, Afterwards test switch. Okay, that's project working set. Huh. Oh, no. Okay, Colgraph, hands-on, finish. All right, there we go. So now let's see. Hopefully this will work. So now you should see my Mac, I hope. Let's see if that will work. There we go. Oh, no, you shouldn't see this. So, since I'm going to actually show this so that you can see what I'm actually seeing right now, if you do have any questions, I won't be able to see them on the text chat, so just please use the voice chat or the voice, just use voice basically on the Zoom chat instead of text, because I won't be able to see the chat. Otherwise, you won't see what I'm going to show you here. So, if you look here at this, this is the Colgraphs project that we have from the. Sorry. You can't see or what? Okay, maybe I'm not. I thought I heard somebody saying something, but anyways. So this is the ColeGraphs. This is the ColeGraphs project from the hands-on repository that I linked on the GitHub on the Zoom chat. So if you go to the main method here, this is basically the. Sorry, I'm just making some space here for myself. So this is basically some code that I wrote to be able to run ColeGraph analysis. So the first thing that I do here, this line here, is basically get the absolute path to the bin directory, which contains the class files of the current project that I have, because the current project is going to contain class files that I want to analyze. The second thing is I do have some Java runtime environments that I want to analyze. Remember, like when we do a whole program analysis, you don't only analyze your binaries, but you also need to analyze the library dependencies. So the GRE is one of the major ones. So I'm adding it here with a version number. So I do have here, for example, like a folder where you can see Java 1.4, Java 1.6. So this is basically what that GRE version is. And here I am having a string that is comma separated values of all the relevant paths related to the GRE in the absolute path to the GRE runtime directory. So I'm basically getting all the jar files under this path. Forget about Averroes for now, we'll get to it in a minute. And forget about placeholder for now, we'll get to it in a minute. So we're just going to turn this to false. And here we're going to look at a hello world example. So what is the hello world example? This hello world example is as follows. So if you look here, where is my hello world example? It's right here. So this hello world is basically just a string hello world that I'm printing out from my main method in Java. And I want to create the ColeGraph for that. And let's see how this will actually pan out. So here I'm using the Soot analysis framework. So the first thing I typically try to do in Soot is calling g.reset. G is the global variable, so I'm resetting all the global data structures that Soot has so that I don't have to worry about any stale information from a previous analysis run. Then in Soot, you need to set some parameters before you actually run the analysis. So first, you need to tell Soot what classes do you want the Soot analysis framework to analyze. So I'm telling it you should analyze the main class, which is that class here, hello world. This is really my main class. Forget about Averroes for now. And then I need to also set the Soot class path so that it can search for classes that are dependencies of anything that it finds in my main class. So there I would put the bin directory, the GRE files, so that if I'm calling, for example, in hello world, I'm calling JavaLang system. Where do I find that? Soot will ask, where do I find JavaLang system? I need to tell it you can find it in a class along this Soot class path. So that's going to set the Soot class path for you. Then I need to set the main class, because this is going to tell Soot how it's going to find the entry points of the program, or one of the ways to do that. Then I'm going to run a whole program analysis. Remember, like when we did the ideal ColeGraph diagram and we can't compute that, so we resort to a whole program analysis instead. This is what this is going to do. So we need to set the whole program analysis to true. Then the most important thing that would tell Soot to start loading those classes is calling load necessary classes. So this is a really crucial method call that you need to do before you get to analyzing anything else afterwards. Then you're going to set the main class from options. You can only do that after loading necessary classes, because this call here is going to look and search for the main class in the set of loaded classes. So if you haven't loaded them yet, it's going to find an empty set, so it's not going to be able to find it there. There's also some other way where you can set entry points, but we're going to get to that when we talk about Averroes later on. So I just have some auxiliary functions here, or helper functions, that just tells Soot to run CHA or RTA or VTA or Spark, and a few helper functions also for you that will dump the call graph and it will dump the pointer assignment graph as well, so that we can see what the results are. So just apply CHA is as simple as running this transform in Soot. So right now, I'm gonna run this on my desktop machine to run CHA on this Hello World program, and I would like you to take a guess, like, and please tell me through voice, like I said, because I won't be able to see the text chat. How long do you think Soot will take to generate the CHA call graph for this example here? Right. I hear somebody's trying to take a stab at it. So tell me, like, is it in the order of minutes, seconds, 100 seconds? What do you think? Anyone? Yeah. Yeah, I can hear you. It's just one print statement, right? Like, what could possibly go wrong there with one print statement, right? So let's actually try, yeah, yeah. Right, yeah, because, so it is one print statement, but to get to that print statement, I need to know what this out is. Oh, and this out, like, if you can, I don't know if you can see that from the pop-ups that show up on an Eclipse here, but this out field is a print stream. So suddenly now Soot needs to figure out, oh, what is print stream? And print stream happens to be a class in the library in the JDK. And to get to that, I need to know actually JavaLang system, because this is a field in JavaLang system. So it's not as simple as just, yes, it may seem as simple as just one print statement, but there's a whole bunch of things happening there that Soot also as an analysis framework would need to analyze. So let's actually try to run that and see what happens. Yeah, proceed. It's error in another project, not this one. So it is running, and it ran at 9:22:04. Why is it not showing any output? Why didn't it show other output there? It should show other stuff. Just give me a second here. Well, we can actually sort of figure it out from here. So it started at 9:22:04, finished at 9:22:28. So it took about 24 seconds just for Soot to analyze this single line of print statement. And the main, that's not, I mean, that may be, yeah, okay, there is a whole bunch of libraries, there is a whole bunch of classes we need to figure out. But look at the call graph. How many edges there? 162,779 edges in this call graph. Right? Does this seem right to you? Like, yep. Right. So that's one way to think about it as well. But the other way to think about it is if you look at so this is the dump of the call graph actually, just from the main method. And these are the points two sets of the variables in the main method. And you will see that R0 is basically R0 is basically the first parameter, and $R1 is going to be the internal local variable that is for this system.out. So if you look here at the types that in CHA, remember, like we're doing this as a CHA analysis. So it will basically, R0 will be any subtype of Java-Lang object, which pretty much says it's going to be any type that you're going to get in your program. So that's kind of imprecise, right? So that's going to basically be any object you might actually encounter is going to conform to this any subtype of Java-Lang object. And the same for R1, because R1 is this system.out. It's declared as a print stream. So if you look only at the class hierarchy, you're expecting this out field may get any subtype of Java IO print stream, which is a whole bunch of them. And just by having those two variables, looking at the class hierarchy of the objects only, which include a whole bunch of SDK files or Java runtime files, you're gonna get 162,000 edges in there. Some of them or many of them are just useless. They don't even exist if you look at the main method. They happen in the library, they happen between interactions between library methods. They have nothing to do with the library, with the application code itself. And this is really where you can see how imprecise and sometimes useless class hierarchy analysis is, without having to play a little bit more tricks. So, well, CHA is not that good, we know that. How about RTA? Let's have it a bit more precise. So we're going to run it again. And I'm just going to mark this because the error is in a separate project than this. I'm going to run this time, but I'm going to run it with RTA. So RTA, basically, I need to set up a few more options here. So I need to say, well, just enable RTA, and I'm going to use the built-in on-the-fly call graph construction algorithm to be false, so that I don't actually use that. I don't use the propagation-based call graph. And I'm going to use RTA as my option. And in Soot, starting from RTA, so RTA, VTA, and Spark are all implemented using the same transformer, the same algorithm. Again, this is one of the really nice things about having a standardized algorithm, that you can configure it with multiple options, and then you can sort of change it as much as you want, so that you can reuse the same algorithm over and over again. So we're doing the same thing here. So here we took a bit more time. So almost 1 minute for the analysis to be done, RTA. And it really didn't help us that much. But the thing that you can tell here is, if you look at the points two set of R0, now we are getting more specific objects, right? You can see that these are going to be the objects that are actually instantiated in the program. Yes, some of them or most of them actually are not in our application code, but these are the ones that are being instantiated even within the library. They are no longer any subtype of Java-Lang object. They are no longer any subtype of Java IO print stream, but the explicit objects that are instantiated. So rather than just looking at the class hierarchy blindly, we're looking at the class hierarchy, but we also are filtering them out based on which objects from that hierarchy have been instantiated and which have not. So it is giving us a little bit more precision with the points two sets. But again, if you look at the edges out of the main method, we didn't really get much benefit there, because the edges are exactly the same. So yeah, that was nice, but not really something that shows the benefit of doing more precise analyses. So let's actually do VTA on the same Hello World program. So the analysis started at 9:28. It keeps running and running, and it's finished at 9:29. Okay. So again, like, points to set of R0 is exactly Java lang string, right? So now we got the exact type of the object, which is here, Java lang string, great, Java lang string array, that is. And R1 is Java IO print stream. So our points to sets are now the most precise they could ever be. But again, that did not affect the call graph in the main method. So maybe the hello world example wasn't that useful here to show off the differences between the precisions. So let's actually find a different example that may show us the difference a bit more. So here I'm showing you another example, which is the collection API. This is exactly the example I showed you on the slides. Remember in the class, in the last lecture? This is exactly the example that we have seen in the class in the last lecture. So in order to run the analysis on this example, all I need to do in this code, the setup that I have here would make it easy so that you need to only change the name of the main class. Everything else stays the same. I only need to change the main class. And I'm going back to run class hierarchy. So here I would expect to find a whole bunch of classes that are of no use that will show up in the call graph. And let's have the example here right in front of us so that we can see how things are in the actual code. There we go. Remember that list of classes that I showed you in the class before? This is why you're getting that. Because R0 is any subtype of Java lang object, which is fine. I mean, it's not fine in the sense that it's really imprecise, but it's not really what we're looking for. What I'm looking for is this C object here. What this C could point to, which is R1 in the intermediate representation that Sut is looking at. And it's going to be any subtype of Java util collection. This could be basically any collection that I have access to in the classes that Sut has access to here. So if you look at the potential edges out of the main method, you're going to see, well, you're going to have multiple edges, potential edges that is, one to priority queue, one to abstract list, one to secure set, class set, entry set, checked entry set, linked list, util $2, which is probably some anonymous class in some native code, array list, abstract collection, as LIFO queue, hash set, set from map, tree set, array queue, and so on and so forth. Basically, every single class that you may possibly call that is a subtype of collection that has the method add in it and exists in the classes that Sut analyze. This doesn't make any sense. I shouldn't have all these edges coming out of the main method here. So let's see, now that I'm going to run not CHA, I'm going to run RDA. So looking at the code here of that collection class, what do you think the methods that could be called from that main method here, at this statement here on line 11? Which add methods do you think should be called, if you recall what RTA does? So my question is, if you recall what rapid type analysis does, or RTA, at this statement here, what are the potential methods that could be called at that point, at this call site? Right, because these are the only objects that are created here in my program that has that are subtypes of collection and also have add as a method declared in them. So this is exactly what RTA does. It would still look at the hierarchy, but it will limit it or constrain it only to those objects that are constrained in my, created in my program. So instead of having all those methods as potential targets, I should only have 2 of them. So let's run RTA. So I'm going to change this to apply RTA, and I'm going to run this again. And we're going to see how long this will take. Hopefully around the same time, maybe. Almost a minute. So that didn't work so much. That's weird. Why that is the case? So if we look at this code here, even though I'm running RTA, and I'm only limiting myself, potentially, to only those objects that I'm creating here, but I forgot one important fact. Remember that when the analysis is running on your code, it doesn't just analyze your code that you wrote, but it analyzes your code along with all its library dependencies. So what are the library dependencies of this code? Well, this code is importing a whole bunch of Java util classes, and there might be in any of these classes, or maybe in Java Lang system, Java Lang string, all the other things that this program may refer to, there might be other objects that are created that you're just not seeing in your code. So the analysis will also have access to those, and they will be considered as instantiated objects. So you will see objects that are of these types here. All these types are instantiated. Admittedly, not all of them in your code, your application code, but many of them are in the library code that you're not seeing. So you always have to be aware of what are the library dependencies that I'm including in my code, because they might have drastic effects on how your code is being viewed by analysis frameworks, or how your code is going to be analyzed by analysis frameworks. And on the other hand, now I'm actually getting exactly the objects that I'm creating here. So all the objects that are being created are flowing to my variable C. So RTA didn't help that much here. Maybe VTA would, because VTA, variable type analysis, actually tracks the pointer assignment, because we create a pointer assignment type assignment graph or type propagation graph. So that potentially would be more precise, because it would exactly figure out that, well, anything of those objects that are being created doesn't actually flow to this C variable here. Only two of them may flow here, which is array list and hash set. So let's run actually VTA and see what happens. So the previous two analyses, CHA and RTA, took about 1 minute each, or 1 minute 10 seconds each to run. Let's see how long VTA would run for. And to run VTA analysis, we run it in a similar fashion to RTA, only in this case we are going to say enable VTA to be true, and we are going to use the on-the-fly call graph construction algorithm here. So now we finally get a reasonable result. Now if you look at actually the time taken, it took only about 20 seconds actually to run. So even though that the analysis is more precise, it took much less time, almost half the time, to run the more precise analysis. So this kind of also, like, there's always a myth in program analysis sometimes that if your analysis is doing more work, it's going to take more time, so it's not going to be scalable. Sometimes actually the more work that the analysis does enables it to reduce the computations that it eventually will do, so it can actually scale up to larger code bases. So this is a clear example of that. So the analysis is doing more work. It's tracking all the assignment statements and the pointer assignments and the type propagation, and creating the type propagation graph, strongly connected components, propagating types across these strongly connected components in the graph, and it still managed to finish in half the time as the naive analysis CHA or RTA. We got exactly the results that we're expecting, that R0, which is basically that arguments, args here, is Java Lang string array, yes. R1, which is that C here, is basically JavaUtil hash set or JavaUtil array list. Perfect. This is what we're expecting. And R2, which is basically that LM here string, is of type JavaLang string. And if we look at the edges coming out of the main method, we have exactly one static invocation, which is basically that call to make collection. And this has been constant in all of them because it's a direct method. On the other hand, that virtual call here, we have two potential methods that could be called. What are they for? They are exactly for array list and hash set. So VTA is actually the necessary and the required analysis here in this example to be able to get the most precise result. Just for fun, I'm going to run the Spark analysis for you so that you can see how long it will take and whether we know that we can't get any more precise results, but whether that more work that the analysis will do is worth doing or not. So even though in the case of VTA, the more work that the analysis did was worth it because it enabled us to scale up the analysis even further, here I took the same time, it took the same time, 20 seconds to run on that code, didn't get any different results, it's exactly the same result I got, but I did a lot more work. So maybe on a small code base like this or a small couple of lines of code that are trivial, naive lines of code, it's fine, but on a large code base, this will take significantly longer than VTA. And this was the example from the collection API that we had in the class. Do you have any questions about this so far? I'll just switch to cam just to be able to see if anyone is asking questions here on the Zoom chat. No? Alright. Okay, so before we go, I do have one more example that I would like to show you that sort of will tie in what we talked about in class today with some of the research that my group is doing. Just give me a second to get back to this. All right, so remember this option is Averroes. So back in my PhD days, I did some work on summarizing library dependencies so that we can create a very an over approximation that is precise enough for that library so that we can use that over approximation in any analysis framework without having to analyze those library dependencies. So basically enabling the analysis only to focus on the application part of the program and have a rough idea or a rough estimate of what the library is doing that would enable the analysis to be really fast in running on the program. So to showcase that, I am going to run it on Java 1.6 and I'm going back to the simplest hello world example. I think that's it. And is Averroes is false, so I'm disabling my tool there, and I'm gonna run the apply Spark. So I'm gonna run Spark. I'm gonna run that, and let's see how long it will take to analyze the full program, the whole program, standard way, and see how long it would take and see what the result would be. And then compare that with enabling Averroes, the summarization tool that I built back in my PhD, and see how both would compare in terms of performance and results. All right, so this one here took about, what is that? 30 seconds, maybe 33 seconds or so to run. So it took about 33 seconds to run on the hello world example on this simple print statement. You have a call graph that has almost 94,000 edges. We have a couple of edges here. They are all fine. You have a print statement to hello world. Where we have a static initializer to JavaLang system and static initializer of JavaLang object. And you have a virtual call to the print statement in the print stream. The print line statement, sorry, in print stream. So far so good. And we have a pretty precise result for the points to set for R0 and R1. So this one here took 33 minutes, 33 seconds. Assuming that we already ran Averroes, which takes few seconds to run, I'm going to just enable the summary for Averroes just by turning this flag to true. And I'm going to run Averroes now and see if I'm running the analysis using the summary of the library instead of analyzing the original library, how long would the analysis take to run on the same line of code, on the same piece of code? So if the original library, when analyzing it, took 33 seconds, how long do you think analyzing the summarized version of the library would take in this case? Do you venture to take a guess there? So 33 seconds for the original library. My question is, how many seconds do you think it will take for the summarized version of the library? Alright, maybe I should just try to run it and see how it goes. There we go. That took exactly 1 second there. From start to finish. So almost 30 times less, almost 30 times faster than running the original library or analyzing the original library. I have a call graph with much fewer edges because I'm basically ignoring anything that is irrelevant to my application code within the library. I have the same number of edges. I have the same actually edges, not just the number of edges. I have the same edges in my application, which I care about. So the 2 calls to the static initializers and the virtual call to hello world to print stream. I have a lot less or a lot fewer var nodes and field ref nodes and alloc nodes. So these are the nodes in my pointer assignment graph, if you recall from the lecture last Tuesday or Tuesday. I have the same points to set for R0 and same points to set for R1, so that's why I'm not losing any kind of precision for these application variables, and my application edges are the same. But I significantly improved the performance of the application, of the analysis. In fact, in the experiments that we've done a few years ago, the improvement in the performance is substantial enough that we can analyze code that depends on the Java SDK, and the size of the summary that we generate is about 600 times smaller. It causes the analysis to be about 12 times faster and uses about 7 times less memory than analyzing the original library code. So this goes along some of the research that my group is currently doing. So I have a few students in my group now working on summarizing code such that you can have those reusable summaries. You only generate them once and then you can reuse them again in any kind of analysis to be able to analyze code on a large scale that is prohibitively expensive to analyze otherwise. And have a whole bunch of students that are working on various things related to that as well, like how we can scale pointer analysis, how we can build more efficient analyses that are related to just-in-time compilers based on static analysis, how we can build and verify patches or code repairs that are related to crypto APIs, how we can formally verify those patches and make sure that they don't tamper with program semantics, and so on and so forth. Be happy to talk to you more about some of the research that my group is doing, maybe offline or some other time. But these are some of the examples that I wanted to run by you today in the lecture, so that you can see hands-on what is the difference between CHA, RTA, VTA, and Spark, with the various examples, a few examples there, more concretely than just the examples that we have been discussing in the lecture. All the code, like I said, that we have went through today, exactly those projects are available to you on the GitHub repository, so please check it out. Try it out yourself, change the configurations, try out other configurations, see for yourself how those analyses are different from each other. And if you have any questions, please don't hesitate to talk to me or talk to Ifaz about it. And that's all I had for you today. Do you have any questions for me? Yep. No, actually. So in my PhD thesis and later on in a few years after that, we actually formally proved that the analysis will be sound. And we have a mechanized proof using a proof assistant, a theorem assistant prover called Coq, that has been developed by INRIA in France. And this is typically used in programming languages to prove formally, with machine-checked proof, that certain soundness properties exist or are preserved in certain analyses or programming language properties, or for a programming language, sorry. So we formally proved that the analysis would actually be sound. The thing that we went through with this analysis here with Averroes is sometimes the analysis, to make it sound, it gets too imprecise that the trade-off is not worth it anymore. And we have seen that already with some client analyses that need more precise data flow analyses, like taint analysis, for example. And we're going to talk about that actually in class in a couple of lectures when we talk about IFDS and IDE. And these kind of problems are the kind of research problems that one of my current students, David Sekas, is currently exploring, is how we can make these library summarization techniques more precise, but still sort of keep that good balance between precision and safe over approximation, but still make the analysis performant enough that we can benefit from this summarization to make it more scalable, rather than just like running it for more time than just analyzing the original library, because otherwise it wouldn't, it's not going to pay off if you take the same time as analyzing the original library to generate that summary. Hope that answers your question. Cool. So, well, okay. So we are a few minutes over the class time, and I don't want to keep you longer than that. So that would be all for today. I hope you enjoyed today's lecture with a little bit more hands-on experience than the previous lectures. Like I said, the code is all available for you on GitHub. Please try it out. Have fun with it. And hopefully you'll have a lovely weekend. And I will see you on Tuesday next week. Thank you, everyone.